This is Chapter 10. What I said in class about Chapter 10 is it is a bit of a trickier chapter because most of the concepts that we're going to be talking about are conceptual. So there's a little less math that we're going to do for this chapter and a little bit more thinking through the ideas. So I highly, highly suggest this is a chapter you read. If not once, then like 4 times. That starts out with intermolecular forces. Intermolecular forces are the forces that occur between molecules. That would be different than intramolecular forces. Intramolecular forces are the actual bonds. So, for example, an intermolecular force would be a dipole-dipole force, and one of those would be hydrogen bonding. Now remember, a dipole is essentially a polar area of a molecule, and it's an uneven distribution of charge. London dispersion forces we're going to talk about, but is in another situation or another example of an intermolecular forces. Intramolecular bonds are stronger than intermolecular forces, and that should make sense. It's easier to disrupt the hydrogen bonding between molecules than it is to disrupt the polar covalent bond within the molecule. Importantly, that one idea that is important to understand is that the lower the boiling point, or this could also apply to vapor pressure or melting point, the weaker the intermolecular attractions. The higher the boiling point, the stronger the intermolecular attractions, and that's important. So as a review, which are stronger, intramolecular or intermolecular forces, and how do you know? The correct answer is intramolecular bonds. These are stronger because it would take a lot more energy to overcome the covalent bonds and break apart the molecule than to overcome the intermolecular forces between the atoms to make it a liquid or a gas. Speaking of liquid or gases, this is a good time to mention phase changes. Phase changes occur when a substance goes from a solid to liquid or to a gas, but the molecules themselves remain intact. Importantly, the changes in state are due to changes in the forces that occur among the molecules rather than those within the molecules. So you can have a solid to a liquid, you add energy, the motions of the molecules increase and eventually achieve greater movement and disorder, which is characteristic of a liquid. You could also have a liquid to a gas, and this is when you're adding even more energy to reach the gaseous state, where eventually the individual molecules are far apart and not acting very much at all. Water is a little bit, it's one of those, it's a little funky, and one thing that happens with water in the solid state is the hydrogen bonds actually sort of straighten out and become a little stiffer, which means the density of water in the solid state is less than the density of water in the liquid state. And that's due to the amount of hydrogen bonding you have within water, and those hydrogen bonds, when in the solid state, become a lot more rigid. Now, some more information about the specific types of intermolecular forces. You can have a dipole-dipole force, and this is the force that occurs because of a dipole moment. The definition of a dipole moment is molecules with polar bonds often have an electric field because of an unequal distribution of charge. Polar molecules are those that have an uneven charge distribution and their dipoles do not cancel. Compounds exhibiting polar bonds have higher melting points and boiling points than those with more weaker polar bonds. Molecules with dipole moments can attract each other electrostatically. They line up so the positive and negative ends are close to each other. And they're only about 1% as strong as covalent or ionic bonds, so these bonds are not very strong at all. Hydrochloric acid molecules are held together by this type of bond. In HCl, the chlorine pulls the electrons in the bond with greater force than the hydrogen, so the molecule is polar in terms of electron distribution. Then the two neighboring HCl molecules will align with their oppositely charged ends attracting one another, creating an intermolecular attraction. Hydrogen bonding is a special type of bond. It is a very strong dipole-dipole force. It is when hydrogen is bound to a highly electronegative atom like nitrogen, oxygen, or fluorine. And then the hydrogens are then electrostatically attracted to the lone pair on the nitrogen, oxygen, or fluorine molecules. This is the strongest type of intermolecular force. But importantly, never confuse hydrogen bonding with a bonded hydrogen. The unique physical properties of water are due to the fact that it exhibits hydrogen bonding, and as a result of these attractions, water has a very high boiling point, a very high specific heat, and many other unusual properties. And those properties are specifically aligned to the fact that water has so much hydrogen bonding. The final one that we'll talk about in this section is London dispersion forces. Another name for those is induced dipole-dipole forces. Our textbook uses London dispersion forces, but both of the terms can be used interchangeably. These are the force of attraction between two nonpolar molecules due to the fact that they can form temporary dipoles. Essentially, the idea is that electrons are moving, and they are constantly moving, and there's going to be a time in which the electrons are going to be in greater density in one area versus another, and that is what is called an induced dipole. This type of force, a London dispersion force or an induced dipole, is much greater in larger molecules. Importantly, this occurs in all molecules, not including nonpolar ones. Nonpolar molecules will have no natural attraction for each other, but this intermolecular force, London dispersion or induced dipole, does happen. Another important fact, without these forces, we could not liquefy covalent gases or solidify covalent liquids. And let me just say one more thing about that. If we did not have intermolecular forces, we could not have phase changes, because phase changes involves changing the intermolecular forces between molecules. Okay. Now we're looking at an example of the boiling points for a bunch of covalent hydrides in elements in groups 4A, 5A, and 6A. And in general, the stronger the intermolecular forces, the higher the melting points. This is because there's such a variation in the boiling point among covalent hydrides in groups 4 through 7. One would expect that the boiling point would increase with increasing molecular mass because there's more electrons in the molecule, there's more polarizable stuff in there in the cloud. They have stronger intermolecular forces, but that's not how it works, and the reason why is because of hydrogen bonding. The lighter the hydrides have higher electronegativity values, which leads to more polar hydrogen to the other bond. Increased polarity means increased attraction, which means stronger attraction for the hydrogen bonding. So essentially, what I'm showing you here, and I just said a whole lot of words, and you might be thinking to yourself, I don't even know what's happening. But in general, what we're looking at here is a trend in boiling points. And in general, you would expect these to get bigger with increasing size. So you would expect these lines to not have a weird, funky check shape. You would expect them to be straighter. And the reason why these lines are not straight is because H2O, hydrogen fluoride, NH3, these things all have hydrogen bonding, which gives them exceptionally high boiling points, even though they are not very heavy. Okay, next up. Which molecule is capable of forming stronger intermolecular forces? And explain. Give you a second to think about it. You should have said that H2O has stronger intermolecular forces, and this is because it exhibits hydrogen bonding, whereas The other one will only exhibit London dispersion forces. Okay, next up. This one I'll read the question explained, but I want you to pause it and give it a try. The question is, draw two Lewis structures for the formula C2H6O and compare the boiling points of the two molecules. So you need to draw out the two possible Lewis structures for that formula and then figure out and explain which one is going to have a higher boiling point. Go ahead and pause it here. And in class, remind me to ask if anyone actually ever does pause it well when I say that. But anywho, we digress. Here are the two Lewis structures. You should identify that the ethanol, which is the CH3CH2OH, so the one with the oxygen bonded to the hydrogen, that's ethanol, is going to have a higher boiling point than dimethyl ether, CH3OCH3, the one with the oxygen in the middle, because ethanol can exhibit hydrogen bonding and dimethyl ether is only going to be able to exhibit dipole-dipole interactions. Hydrogen bonding is stronger than dipole-dipole, so it will raise the boiling point of ethanol. And we skipped that one. Finally, this figure here is a flow chart that's worth studying. It is an overall chart to figure out what type of forces or bonding might be exhibited in molecules. And one note, dipole-dipole, induced dipole, London dispersion forces, all of these collectively are called van der Waals forces. And that will do it for section 1.